Grounding transformers sit on the electrical grid as the ultimate failsafe. They provide an artificial neutral point, giving fault currents a safe, predictable path to girth when a system anomaly occurs. An ungrounded fault is a violent event. An intense arc can vaporize metal and cascade through substations in milliseconds. Rigorous, multi-domain testing forms the only barrier against that kind of systemic destruction. Commissioning these transformers requires strict adherence to multiple engineering frameworks, including IEC, IEEE, and NEMA standards. When these codes conflict on a specific tolerance, the governance rule is absolute. The technician must apply the most stringent approved requirement. Before a single meter is connected, the environment must be completely neutralized. This means verifying the lockout-tagout status, confirming temporary grounding sets, and meticulously scrubbing the terminal bushings to remove any conductive contamination or moisture. The validation matrix requires highly precise instruments. The testing sequence relies on 5 kV DC insulation testers, Doble power factor test sets, and calibrated microohm meters. Environmental contamination will structurally invalidate the entire dataset. Testing begins with the physical isolation and sterilization of the transformer itself. The first required testing domain is dielectric integrity. We are confirming that the insulation barrier separating the high-voltage winding from the grounded tank is entirely intact. This diagram details the precise physical connections required for a 5 kV DC insulation resistance test. The test instrument connects across the red, yellow, blue, and neutral terminals to push a regulated DC voltage into the windings. We apply the test voltage and monitor the leakage current, recording exact resistance values measured at the 1-minute and 10-minute marks to observe how the insulation absorbs the charge over time. These readings give us the polarization index, which is the ratio of the 10-minute measurement divided by the 1-minute measurement. The acceptance criteria demands a minimum index of 1.25. Anything lower requires immediate investigation. The core and frame require their own insulation checks. Looking at these callout circles, technicians must explicitly remove the links tying the core, frame, and earth together before applying a 1 kV DC test. As shown in these 3 lower panels, we validate 3 distinct paths: core to earth, frame to earth, and core to frame, ensuring total internal isolation. Because the transformer holds a lethal capacitive charge after DC testing, the manual designates a strict hold point. Technicians safely discharge the asset with a grounding rod and visually verify the restoration of all earth links before proceeding. Dielectric testing mathematically proves the absence of invisible catastrophic paths to ground through the insulating barriers. The second required domain is conductive continuity. Here, the focus shifts to the windings themselves, proving they can efficiently handle heavy magnetic and thermal loads without excessive resistance. This schematic illustrates the DC winding resistance test. We use Kelvin leads, the dual connections bridging the phase and neutral terminals, to bypass the resistance of the test cables themselves, isolating the precise resistance of the copper winding. Raw resistance data to establish a corrected baseline at 75 degrees Celsius. To measure phase impedance, we require a dynamic AC test. This wiring schematic shows how technicians inject a controlled 380-volt, 3-phase power supply directly into the windings. We monitor the asset for abnormal noise or imbalance, recording the voltage drop and phase current. We calculate the final phase impedance using this exact equation. Conductive validation ensures the asset operates predictably under grid loads, preventing localized overheating and thermal runaway within the coils. Standard Megger testing evaluates gross insulation integrity, but it cannot detect microscopic moisture in the cellulose paper or subtle chemical contamination in the insulating fluid. This panel illustrates the Doble power factor, or tan delta, setup. We apply a 10 kV alternating current to the terminals and measure the slight capacitive charging current and watts loss leaking through the insulation. As highlighted by the magnifying glass, the exception criteria is exceptionally tight. A power factor exceeding 0.5% requires an immediate investigation into the transformer's internal state. Technicians also draw samples to test the oil dielectric breakdown voltage. This requires purging the test cup with a hydrocarbon solvent, eliminating microscopic air bubbles, and applying an escalating voltage ramp until the fluid arcs, which must occur above a 50 kV threshold. Fluid and capacitance testing catches subtle chemical degradation that solid DC resistance testing is entirely blind to. The final physical testing domain is systemic protection. A structurally healthy transformer core will still fail if its internal protection logic is deaf to grid anomalies. These split diagrams show how we calibrate the physical sensors. We immerse the oil temperature probe in a heated fluid bath to verify its dial, and inject secondary current into the capillary circuit to simulate the thermal rise of the windings under load. This table catalogs the critical relays tied to the marshalling kiosk, including the book holes, rapid pressure, and temperature devices. We physically simulate each contact to ensure they trigger the correct alarm and trip sequences. Looking at diagrams 7.1 and 7.2, we evaluate the auxiliary cooling fans by purposefully dropping a single phase. We measure the starting and running currents to prove that the single-phasing protection circuit recognizes the imbalance and isolates the motor. Verifying that local physical trips correctly match the remote SCADA event logs guarantees the grid operator will see a fault in the control room before the transformer fails in the field. Field commissioning rarely produces perfect data on the first pass. Engineers must actively interpret the measurements and troubleshoot the specific failure modes exposed by the testing matrix. A polarization index failure below 1.25 is a primary diagnostic flag. If we rule out external surface tracking on dirty bushings, this low ratio points to internal moisture infiltrate in the cellulose insulation or a compromised vacuum seal in the oil tank. If the winding resistance test yields wildly fluctuating numbers, technicians evaluate the setup. They must determine if it is a simple contact error with the Kelvin clamps or evidence of a catastrophic internal tap connection failure. An elevated tan delta reading requires similar scrutiny. A high power factor can result from parasitic capacitance if the test leads are poorly routed near grounded metal, or it can indicate genuine, irreversible degradation of the insulation paper. The final diagnostic barrier is protection logic misalignment. If a physical trip at the marshalling kiosk fails to generate an event log on the remote workstation, engineers mandate an absolute block on grid energization. The grounding transformer gives the wider electrical grid its ultimate safety net. This exhaustive, multi-domain testing matrix is the only way to ensure the net itself has no holes.